Hello, Internet. We are live.
Hey everyone, welcome to episode 65 of the Stanford MLSys seminar series. I'm Kern, and as always, we have with us Stan,
Hey.
Fyodor, Piero, and our guest today, Alkis Polyzotis from Databricks. So just a little bit about this seminar. So as always, we're going to do a 30-minute talk followed by a 30-minute podcast style discussion where you in the YouTube live audience can ask questions and chat, and we'll get those questions across to the speaker. During the talk, you can also keep those questions coming, and we keep track of them, and we ask them during the podcast. So we'll not disturb the speaker during those 30 minutes. And in some personal news, before we get into the talk and the podcast, I want to congratulate Piero on coming out of stealth with his company Partybase. So Piero, you want to say a couple of words?
Yeah, thank you very much, Karan, for that. Just wanted to say, we're coming out today. We are, introducing this new idea of the declarative machine learning platform, and we published an article on Medium, like a blog post, that you can check it out if you like. And there's also a TechCrunch covered our story, which is very, very nice. And there's also this new website, partybase.com, that you can check out if you're interested in knowing more about what we've been building on top of the open source technologies of Ludwig and Harvard.
Awesome. Well, congratulations, and we're excited to see the rocket ship start. So yeah, I guess moving into this seminar, our guest today, Alkis Polyzotis, is going to be talking to us about what can data-centric AI learn from data and ML engineering, and covering kind of this pretty exciting topic that has been getting a lot of I think people in the industry excited. So a little bit about Alkis. He's a software engineer at Databricks and works on data management and machine learning. Before this, he was at Google as a research scientist and a professor at UC Santa Cruz, and got his PhD from Wisconsin at Madison. So take it away, Alkis, whenever you're ready.
Thank you, Karen, for the intro, and thanks for the invite, and thanks to the audience for joining. So yeah, the title of the talk is about data-centric AI and data and ML engineering, and what we can transfer from one to the other. So let's try to unpack this a little bit. So data-centric AI, first of all. Hold on, let's see if I can figure out how to advance here. Sorry. Okay. So this definition for data-centric AI is something that I lifted from the call for papers from a recent workshop at the NeurIPS. So according to this definition, this is representing the recent transition from focusing on modeling to the underlying data used to train and evaluate models. So this transition is not very surprising. Overall, we've seen several optimizations to training algorithms. We've seen AutoML become more and more robust. So it's natural that we shift our attention from optimizing the algorithm to optimize against input over the data. At the same time, there is not just data-centric AI. For many years, we've seen data-centric applications in general, right? In every major organization that you go, you'll see a bunch of these data-centric applications running and being sort of a core part of the business. For instance, a utility company needs to run and maintain its usage records to bill its customers, or online stores, they need to maintain purchase data to train recommenders, mine for customer behaviors. In all of these cases, data management and the curation of data is at the core of these applications. And data and ML engineering have sort of become established disciplines that can help to build and maintain these high quality data sets. And these disciplines have been validated through a wide range of production deployments. So we sort of have some faith that all of these tools and methods that have come out of data and ML engineering are battle tested, right? They can stand the test of production. So given now that if we look at data-centric AI and these data-centric applications, high quality data sets lie in their intersection, and given that data and ML engineering have helped with this, on one side, the question is, what lessons can we transfer over to data-centric AI? And maybe, what sort of new disciplines akin to data and ML engineering do we need to develop on the side of data-centric AI? So this talk basically focuses around some of these lessons that we believe we can transfer over. And these are listed on the slide. Now, I want to say that I will not claim that this list is exhaustive by any means. These are just lessons that we learned or we encountered from our experience in building and deploying infrastructure for data-centric applications. And we also found a little bit surprising, right? So I think that's worth mentioning here. Now, this is largely based on joint work that we did with Matei, and there's an accompanying paper that we published in the Data-centric AI workshop in Europe. So I'll point to that later. But at some parts of the talk, I will also pull in some information based on previous work by colleagues, both at Databricks and at Google, when I worked on the TensorFlow Extended platform. And I'll also spend a little more time on the third one, data monitoring, since this is something that I've worked on quite a bit. Okay, so what I'll do throughout the talk is sort of go through these lessons and try to contrast what usually happens in every case with what we see in production and what are the implications for data-centric AI. So let's start with the first one. Data and AI applications must be updated continuously. Let's start with what I think is a common assumption, which is that usually we're focusing on one-time data preparation. Let's consider the example task of building some system that can diagnose patients from CAT scans. Okay, so we're going to assume that there is some machine learning involved here. Now, a common workflow, if you were in a research setting around this task, would be to gather the CAT scans, work with human annotators and domain experts to annotate them, curate the data set, maybe run it through a few models to convince yourselves that it works adequately well for the task, and then release it to the community. And this is a good thing, right? We can facilitate further research and so on. But overall, the focus here is that we're expending quite a bit of human effort to generate one high-quality data set for a particular ML problem. And if we shift our focus to what happens in production, usually we don't have one-time data preparation, but sort of a continuous data preparation. So both the task and the data definition can change over time. And this can happen for many reasons that are not easy to control. For instance, going back to this CAT scan application, we might have new machines that are deployed in new locations, and now they start bringing us new data that might itself carry its own biases. Or our existing machines receive the software update, and this changes some of the data we can get from them. Or maybe we even change the task itself. For instance, we extend the labeling ontology because we realize that we can diagnose more diseases than we started from. In all of these cases, the data will get updated, and we'll have to accordingly update downstream artifacts. For instance, the models we build or any derived data sets. So overall, we're shifting from one-time creation to creating high-quality data sets for an evolving ML task continuously. Okay, this is the big difference that we've seen in production. Let me offer some supporting evidence for this on this slide. This is based on a study that we did at Google, where we sort of observed close to 3,000 pipelines in production for machine learning over the span of 4 months. Okay, so I'll point to the detailed report towards the end, but I think these two charts show very nicely this dynamicity in the system. On the left chart, what we have on the x-axis is the lifespan of a pipeline, which is basically how long has a pipeline been active in terms of receiving data sets and training new models on these data sets. And you can see that even though the majority of the pipelines is on the left of this x-axis, so they're relatively short-lived, it's 1 or 2 days that they're active, most of them are actually on longer lifespans. So we have some pipelines that have been active for the whole duration of our study, for the whole 4 months. The right chart shows a different view of this dynamicity. We're basically tracking the number of times per day in a pipeline that the trainer executes. And in these pipelines, the trainer executes when new data sets arrive. So again, you can see that most of the pipelines are in this once per day execution. So there is only one new data set per day that comes in, but we also have pipelines that execute up to 800 times a day. And this gives you a sense of the volatility of the data. Now, of course, this highly depends on the domain. So it is true that for those 800 times a day, we're mostly talking about pipelines that are doing some kind of fraud detection or spam detection, so they have to be updated continuously. But the point is that these setups do exist in production. So given this dynamicity, what does this imply for data-centric AI? First of all, because data is so dynamic, we really cannot afford to have humans in the loop too often, because humans cost much and human attention is expensive. And also humans are slow in what they do, right? So we need to automate processes as much as we can, and this covers both data collection and labeling. And the moment you start automating, you need to have good monitoring in place so that you can catch errors early. It also means that we have to favor algorithms and workflows that can accommodate this changing setup, right? So for instance, weak supervision with labeling functions is great if we're dealing with changing prompt definitions, because we can sort of rerun the same labeling functions over the new data. Or when we have a changing data schema, for instance, going back to our scenario with the CAT scan machines, suppose that a software update starts recording more data. Now we have a different schema. We want to train models and serve models on the schema. We have to be careful how we propagate these updates to the schema. Otherwise, we can break existing models that exist in production. So we have to be a little bit opinionated about how these things happen. And of course, we're going to be dealing more often with a mix of old and new data. So we need, again, workflows that allow this and allows us to blend between the two. All right. So let me move to the second lesson. Production deployment workflows are often code-centric. And again, let me start with what I think is a common assumption, which is not code-centric workflows, but model-centric workflows. And in this case, what you see in the diagram is you have a data scientist. They're working in some development environment, and they author training code that they'll use to train a model over some data. And once they evaluate the model and they convince themselves that this model is good, then they're going to publish this model to production. And that's the point where the model goes live and starts getting used by production requests. So the whole idea is that the model is the main artifact and what is transferred between development and production. However, this is not what we see in production teams. Production teams seem to favor this code-centric view. And if you look at the diagram now, the difference is that the data scientist is still working in the development environment. They're still authoring the training code. But now it's the code that gets transitioned over to the production environment. And at that point, an ML engineer is responsible to take that, run it over production data, and generate a production model that will then be deployed and go live. So the main artifact here is no longer the model, it's the training code. Now, there are a couple of reasons why this is favored. First of all, this allows ML engineers to control what I'll call the build environment, which basically contains everything that you need to train a model. So it contains data dependencies, and infrastructure dependencies, and also any software dependencies, for instance, down to the version of a machine learning library that you have installed. And by being able to create the model in production by just running the training code, the ML engineer can make sure that the production model is compatible with this production build environment. And it's very difficult for the data scientist to control that on their side, right? The data scientist might use features that are not yet alive in production, or they might use libraries that are not allowed in production. Under those cases, you could have production outages if you just use the model that the data scientist generates in the development environment. But another point that is important and is linked to the previous lesson is that by having the training code in the setup, the ML engineer can retrain the model as needed, right? So they can apply that automation that we described earlier when you have evolving data sets. So what does this mean for data-centric AI? Well, one thing to note here is that this build environment can itself be dynamic. The ML engineers might install new ML libraries, or they might deploy new hardware that is used for training or serving. And every such update creates a new build environment that doesn't necessarily replace the old environment, okay? And in the meantime, data sets keep getting updated and they kept getting used in these different environments. So we end up with what we call a multiverse of evolving data sets in the same system. And this can become a little bit crazy or maddening, as you can imagine over time. So we definitely need platforms in place for data-centric AI that can manage the multiverse. They can track the different universes that exist, where again, every universe sort of corresponds to a build environment and the data that is used within it. And they provide isolation and tracking between these environments. One interesting exception here is labeling. So if we want to have human annotators and we try to separate them between development and production, that might end up being too expensive, right? So there are cases where you might want to try out some experimental labeling UI in development, but then use the same labels in production if you can convince yourself that these are actually good labels, or not used in production if the development, if the new labeling UI ends up being not as good. So in this case, it's important to allow labeling to blend between dev and prod, but you need to be able to track lineage of labels back to annotators and back to the UIs that they used. All right, so third lesson, data monitoring must be actionable. It's pretty obvious that data monitoring is important, both in data-centric AI and in these data-centric applications, right? But what I would argue here is that monitoring goes beyond just alerting, which is the common assumption. So if you look at a typical setup for a monitoring solution, the idea is that you define some metrics that reflect data or model quality or distribution shape. Then some human sets thresholds on these metrics that define conditions. So for instance, you can say that if some metric, let's say, the p-value of a distribution difference exceeds some threshold, then that's what I will mark as drift. And then alerts are fired whenever these thresholds are exceeded, okay? And I don't want to downplay this part. This alerting part is still important, and there is a lot of interesting work on robust metrics or on how we can do alerting under different assumptions where we might not have labels, for instance, but we still want to alert on potential model quality problems, or where labels are expensive, but we still want to be able to approximate model quality with some accuracy. But in practice, monitoring acquires two more layers, which are diagnosis and action. And I'll try to explain this through this diagram here. So at the bottom layer, we still have alerting, which is the metrics we define plus any thresholds over these metrics. So I might say, for instance, that I'm going to compute, the chi-square test on country to compare scoring data to training data. And if the p-value is below 0.05, then this is drift for my preferences. Now, once an alert is fired, somebody has to look at this alert in production, and they have to understand why it happened. And this is where diagnosis comes in, right? They try to identify the root cause. So in this case, for instance, they might look at all the data and decide, okay, this is a distribution shift because we started receiving more country from Brazil, okay? So Brazil showed up in the country feature. This is a change in the outside world. So the right action is to take these new requests, label them, and then retrain the model. Now, retraining is a common action that practitioners will take whenever data monitoring signifies that something is wrong, but it's not the only action. For instance, suppose that we have, suppose that we have the same alert, this chi-square test on the same feature, but now in the diagnosis layer, we notice that the distribution change happened because all the country values went from uppercase to lowercase. So the data didn't change at all in terms of its semantics, or its actual distribution. It's just that the encoding of the data is different. And the right thing to do here is not to retrain. Probably this is a bug in the data pipelines, right? So the right thing to do here is to fix the data pipeline and then resume the model. And if you're thinking that this is a very contrived example, let me just say that this is an actual production error that we've seen in a company to remain unnamed. So to design our effective monitoring around this alerting, diagnosis, action framework, I think there are at least the 3 guiding principles that can be useful. The first one is to prioritize for human attention. Somebody has to look at the alerts. So the first thing we need to make sure is that these alerts don't carry a high rate of false positives. If alerts end up being false positive most of the time, they end up being indistinguishable from spam, which means that the human operator will switch off monitoring. So this defeats the whole purpose. Alerts, once they are presented to a human, they also have to provide context that can facilitate the follow-up diagnosis and action. All right. So contrast an alert that just tells you, hey, the chi-squared p-value is below your thresholds, to an alert that tells you a little bit why that chi-squared value is below the threshold, right? So it can tell you that this, lowercase us became more frequent when uppercase was the most frequent. This immediately gets you started on the path to diagnosis. And the last bit here, I don't think this can be overstated, but monitoring must be easy to set up. Monitoring is one of those things where the benefits are long-term. And in many cases, sort of the upfront costs to set up monitoring are not, immediately justified, right? Somebody has to set up monitoring in the case that something bad happens in the future. So we need to make this kind of monitoring systems to be easy to set up so that we sort of lower that barrier for entry. All right, second principle is applying deep monitoring. In this case, I'm not referring to using deep learning for monitoring, although this is an interesting idea on its own, but rather talking about 2 sub-ideas. The first one is that if we just monitor the output of a data pipeline, then it's going to become much harder to diagnose errors. Instead, we should monitor for different points of the pipeline, and then we should use lineage and context to integrate the alerts. So an example on this diagram is a model that's on the right side of this pipeline. So let me try to highlight this. And let's say that we received an alert on this model. And when we open up to see why this alert occurred, we can actually visit the lineage chains and understand that there are alerts over all the data sets that this model is using. So this is immediately useful. Now we can try to understand, okay, something happened much earlier, right, that we try to debug. Moreover, because we know that this is a machine learned model, we might be able to apply context and say, look, we understand that the only important features are coming from one side of the lineage chain. So these are the only 2 alerts that we should be looking at and try to correlate. All right. The second point is that aggregate metrics can hide subpopulation effects. So for instance, we might be looking at the overall model quality and thinking that this is great, we'll have low error rates, but then we might have higher error rates if we look at a slice of the data, say all the data that is coming from a specific zip code. And I'm choosing zip code here because it's one of those features that can leak other sensitive attributes, and you might end up with models that end up being unfair or biased towards some part of the population. Okay, so instead of just looking at aggregate metrics, we should be looking at slice metrics and checking that their trends agree with the aggregate trends. And the last principle that I think can help here is automation. Again, production teams want to automate as much as possible. This agrees with the previous lessons. And there are several ways that we can automate data monitoring. First of all, we can provide some help with the alerting layer, maybe by recommending initial alerts to the user or automatically identifying slices of interest that need to be monitored in addition to the aggregate metrics. We can also provide help with diagnosis. So again, if we have alerting over the lineage chain, we can identify which parts of which alerts across this lineage chain need to be surfaced to the user when alerts fires. And we can also try to highlight which of those are interesting, because in most cases, a user will be inundated with metrics to look at, right? So some guidance here will be useful. And the last bit that we can try to automate is actions. At the very least, I think we should allow for a user to automate the diagnosis and the action after some successful investigation. So if I figure out after receiving an alert that if I see high drift metrics and no other alerts in my lineage chain, then the right thing to do is retrain, then I should be able to put that in a rule. So that next time that this alert fires and the conditions are satisfied, retraining will happen automatically. Production teams are very keen to be setting this kind of automation in place. And of course, we can think about the North Star here, which is a system that automatically learns and recommends corrective actions by observing what a large set of users are doing with the alerts that they receive. This is clearly, a very challenging direction, but it has some interesting open questions in it. All right. So for the last two lessons, I will cover them a bit quicker. For end-to-end versioning, usually it's a no-brainer that you want to version at least your training code. But in machine learning pipelines in production, it is important to co-version all the artifacts. This includes data, the training code, the models, and the build environment in which this code runs to generate models from specific data. And of course, you want lineage to chain them all together. This co-versioning is something that is emerging as a best practice in machine learning engineering, and there are also platforms that provide this out of the box. So if we try to now see what will happen in data-centric AI, we also need to think about versioning. We also need to think about lineage across versions, and this has to work out of the box in the data-centric AI platform because you cannot expect humans to manually tag versions and link them in their manner. So it has to be sort of a side product of the normal workflow in the platform. But in data-centric AI, versioning must extend to UIs and tasks for human annotators. This goes back a little bit to a previous lesson where we wanted to blend labeling between dev and prod. We need to track the versions of UIs and the annotators that work on these UIs to generate labels so that we can make this blending work in production. And the last lesson is that humans might not be allowed to see the actual data. Again, in a typical scenario, when you have a model and some problem occurs on the model, you expect a human to jump in, maybe the data scientist that developed the model, and look at the aggregate model metrics, look at the training or serving data, and make some determination of why the model is mispredicting, for instance, certain examples. But there are some domains in production where this is not possible. The human cannot see or doesn't have any access to the raw data. One example here is, again, from a natural system, is a model that does autocomplete in the context of a messaging application. So in this context, messages, personal messages are considered to be very sensitive, and any access to these messages can reveal a lot of information about the individuals that exchange them. So the solution in that system was that engineers have no access whatsoever to the messages themselves, and now they have to debug the quality of the model, even though they cannot access the data. So what can you do in this case? Well, you have to rely on aggregate info. So you may not be able to get access to the data, but maybe you can see statistics for the data that are not leaking sensitive information again, or maybe rely on proxy data sets. So synthetic data sets that can sort of simulate the data and allow you to essentially run what-if scenarios over the model under different assumptions for the data. There are cases where some access to the data is feasible, but it has to happen through a mechanism where the access is logged so that things can be audited later. And also guidance is important here, because if you have only a few data points that you can access to debug the model, probably you need some help understanding which data points will give you the most bang for the buck. Okay. All right. Now, as I mentioned, this talk is heavily based on a paper that we worked with Matei that was published in this Data-centric AI workshop. The paper explains some of these lessons in more detail and also importantly provides pointers to techniques from ML and data engineering that can be reused for data-centric. The last one is about data validation and covers a little bit of those points that I made about data monitoring. All right, so to recap, the talk basically argued that if we look at data-centric applications and data-centric AI, high-quality data sets sort of lie in the intersection, okay? And by shifting our focus to a production mindset, which is often the case in data-centric applications, we can inform the agenda for data-centric AI. We can also transfer over lessons that data and ML engineering have helped us develop over time in a wide range, again, of production deployments. But what I want to say here is also that this is not just a blind transfer of technology. It's not that data and ML engineering have completely solved all the problems in data-centric AI. What we need to do is take these techniques, treat them as foundation, build on them. And I think that some of these techniques will eventually have to be revisited in the context of data-centric AI. All right, with that, I'm at the end of the talk. So I'll be happy to answer any questions.
Karan, you're muted again.
Thanks so much. Yeah. My little mic here has that blinker, and I always forget to unmute myself. Thanks so much, Alkis, for the talk, and a reminder to folks in the YouTube audience to send in your questions in the chat, and we'll get those across. So I guess to kick things off, one of the things that I was curious about was that example that you had with lowercase country codes versus uppercase country codes, and I guess that got me thinking on a few different questions. Like one was just like for like situations like that where it seems like the data is fairly like it's tabular data, or like not necessarily like high dimensional text or image data or whatever. Are there ways in which we can come up with a little bit more automation in terms of like identifying exactly where the error happened and situating it? And I guess that led me to a follow-up question, which is just that, like, to what degree should we be worried about automating these things so that the false alarm rates and those go up, and like you certainly started having this problem that you probably didn't before, which is that when everything was kind of handcrafted, written out in code for like error checking, then you generally don't have false alarms probably, or they're pretty low. But now suddenly, if you're starting to rely on models and doing kind of more complicated things, you're gonna get maybe misattribution errors, like, oh, the problem is here, but it was actually somewhere else, or there was no error at all, and the model that you were using to actually diagnose these things found errors, but they don't exist. So things like that. I'm just curious, how do you think about those kind of paradigm shifts in terms of how these types of processes should be automated, and what kind of things people should be worried about?
Yep, no, that's a good question. So let me say that if you talk to the practitioners that have to run these systems in production, right, they absolutely want to automate this as much as possible. So I think sort of the ideal system for them would be something that provides monitoring out of the box on all the right points with low cost and with zero false positives, right? Of course, you can imagine that it's everything that I said is sort of untenable, right, to some degree. But that said, I would say that it's good to attack this in sort of a layering fashion, right? So the first thing is to say that if somebody has some asset that they care about, be it a model or data, we first need to figure out how to have sort of localized monitoring on that asset, okay? And we should make it easy for them to get started on that monitoring, on that localized monitoring, through maybe recommending thresholds or maybe learning thresholds, keeping in mind that false positive rate. Once we have that localized monitoring, then lineage comes into play. So now I have localized monitoring of different parts of the lineage graph. Can I bring them together in some fashion of data integration and understand where is the root cause? This is not sort of a pipe dream, right? I mean, there have been studies that have been made in different contexts that try to localize the root causes. But I think what's interesting here is that this has happened mostly in contexts where you can limit the expressive power of the pipeline. So context like I have a bunch of SQL queries that are running, right? So I know that I'm sort of, dealing with this relational algebra setting. So I can use lineage and relational algebra together to reason about effects. Machine learning is a little bit trickier because there's no equivalent of a declarative way to specify what happens, right? In many cases, these pipelines can be arbitrarily complex. And when you have this, you're sort of facing a barrier in terms of propagating information through lineage, either backwards or forwards. I don't know, maybe declarative machine learning can help here. We should be looking into that. But I think the more we standardize on some of these techniques, the easier it will be to sort of automate this reasoning in the lineage chain.
Yeah, no, that makes sense. And I guess, we'll hear from Piero about maybe his thoughts on this too. But I guess one follow-up question, I guess, is in some sense, as you pointed out in your answer, like these things are kind of coupled with what kind of workload is being deployed. Like if you were worried about SQL queries, and if that was the entire problem was just monitoring what's happening with the data and you're running SQL queries on it, then it's a little bit different than if you're doing machine learning. And I wonder whether that changes as well with like large scale models that people are building today, like there's this shift, right, where like people are starting to scale up models and GPT-3 type of situation where you would just have a model that can ingest massive amounts of data and seems much more tolerant to the quality of the data in some sense. So curious about their thoughts there, where like maybe some of these issues in the data pipeline might be mitigated to a certain extent because the models get a little bit better at handling that noise.
Yeah, no, that's an interesting thought. I mean, first of all, I think it's worth mentioning that at least in the current state of affairs, main organizations are still deploying simpler models, right? So for those organizations, it still matters to be able to reason about data errors and effects under this regime of simpler, much simpler models, okay? Now you can argue that, okay, maybe this is the case now, in a few years time, or I don't know how long, everybody will have something like a very complicated model to deal with. I think my gut feeling is that actually this will become even harder, right? Because now you have to worry about or understand why these much more complicated models give you weird outputs. And depending on who has the ability to train these models, now you're dealing with a lot of organizations using a single model that has been trained and hosted in some central place, but all of them are trying now to debug this model from afar, right? Because not everybody will have the ability to train a GPT-3. So I think it will shift a little bit the kind of things that we want to monitor for and how we want to use the signals. I don't think we'll do away with monitoring just because the model has become more powerful, because these models can still give you some very weird outputs, right? Very powerful, but yeah.
Yeah, that makes sense. Thanks for the answer. Dan, Piero, I guess.
Yeah, so thank you very much, Alkis, for the talk in general and also for these considerations. I actually have this interesting example where actually with machine learning is actually almost always more difficult to figure out the problems because of that flexibility that Karan was talking about with respect to noisy inputs. Again, it's a curse and a blessing, right? It's a blessing because it works also with imperfect inputs, but then it becomes more difficult to figure out why, right? That an error occurs. So it's both of them. Actually, one thing that I was curious about is, to a certain extent, the inverse of what Karan was talking about in his first question, which was he was talking about let's not consider more complex types of data, but actually now I'm curious about monitoring for more complex types of data, which could be either like text, the distribution and figuring out the potential errors and how to act on them could be a little bit less straightforward than like a distribution of categorical values, right? And I was thinking both of like more like free-form text and also potentially when there's hidden structure like logs, when there is a structure, but it's not like maybe a regex can parse them, but you don't have that. And also potentially even more complex data types like images and audio, because, more and more also with like data lakes and things like that, there's multiple modalities are coming in coming into play for training models. So I'm curious, what is your take on that?
Yeah, no, that's a great observation. So I think with this kind of more complex data, we're getting a little bit into the territory of deep monitoring that I mentioned, where monitoring now has to break the boundaries of the model, right? And let me give you an example. At least in some cases that I've seen, training over text had a very specific structure over it. You would take the text, parse it into tokens, then train an embedding over these tokens after you vocabularize. So you retain the top K tokens, and then you train an embedding over them. Okay. This was a very specific technique that was used by these teams. It seemed to work well for their domain, but now you have this idea that text comes in, the tokens of the text get mapped to an embedding, which was trained on some distribution of frequent tokens. Okay. Now, all of this mapping happens inside the boundary of a model. So it's invisible to the outside world. So if I were an engineer deploying this model, the only thing that I could monitor for is the text that goes into the model. And maybe I could sort of guess what is the distribution of tokens that I see in the text. Okay, so I can say that the text changes. Obviously, it's meaningless to try to track the distribution of individual instances of text because this will be meaningless, right? But in reality, what these teams wanted to do was to pierce into the model's feature engineering code and say, okay, whatever pre-trained embeddings the model has generated, we want to understand how the distribution changes in that space. Okay, so we want to understand whether the new text we're receiving is matching the distribution of the embedding space that we observed in training versus what we're seeing in scoring. So this required two things. You need to be able to monitor now inside the model, right? So you're sort of taking the model, which is a black box, and you're breaking it up into pieces, and you're inserting a monitoring probe, right, between these pieces that you care about. But it also goes back to what I called about actionable monitoring. So if we just monitor the embeddings and we tell the user, oh, something changed in the embedding space, we don't know exactly what this change represents, but something changed. It's not very meaningful for the user, right? Somebody who's trying to understand why something changed will have a hard time. On the other hand, if you know that the embedding space is defined by this vocabulary of top K terms, then you can do the monitoring on the vocabulary of top K terms. And you can say, okay, what actually changed is the distribution of top K terms, right? The term COVID started being more popular, for instance, at some point. And this is what's stripping up my model. So when you go to this data that has latent information into it, you have to be able to tap into that layer where the latent information gets exposed, but also be careful to do it at a point where the human can understand changes in that layer. Okay, because again, it's one thing to detect a change, and it's another thing to understand why the change happened.
Right, and also what actions to take then to fix it. Also, because again, it's the
exactly
sequence of that. If the average of the embeddings moved somewhere, but you don't have a specific way to go and change it, actionably change something, then it becomes more difficult. This is amazing. Again, I really like the answer. Thank you very much for this. And I think what also makes me think is that to a certain extent, also the definition of what is the data preprocessing part, what is the model, with new kind of models is kind of getting a little bit more blurry to a certain extent, right? I can, speak to my direct experience. Like we are trying to package together some piece of preprocessing within some of the black box package of the model, because that makes particular sense from a computational point of view, but also, that impacts a lot of what you can inspect, what you cannot inspect. So I think these considerations are super, super important.
Yeah. And I think it's, from a best practice point of view, you want to package this computation with a model, right? Because then you can minimize the chances for training serving skew if all this computation happens inside your black box. But then you have to be able to track lineage, I think, a little bit more accurately, right? Because you need to understand what went in the black box and how that is related to training side artifacts. These vocabularies, for instance, that I mentioned in my example, so that then you can make meaningful comparisons between serving time and training time artifacts. So I think that's one case where the argument about versioning and lineage, becomes a little bit, becomes more pronounced, I guess.
100% agree, yeah.
Along sort of those similar lines, one of the things I was curious about, based on your experience with various deployments and pipelines that you've seen, you kind of working at Databricks, if you were kind of is there any sort of kind of high level recommendation or something that you could tell, practitioners who are maybe deploying a machine learning model for the first time or something like that, when they see their models fail or when they see them do something that they don't expect? What's kind of the most common failure modes or the most common places to look that maybe they weren't looking before if this is maybe their first set of deployments?
Yeah, that's a good question. I think based on experience both at Databricks and at Google, I would say you can get surprisingly far in terms of detection by simple checks. Even just saying that this is the schema of my data when I trained the model, and let's compare it to the schema of the data when I serve the model, right? And even if you start doing comparisons on the schema level, you can catch things like feature changing types, which is a breaking change that can happen because in some cases, the serving stack has a different way to generate features than the training stack, and bugs happen, right? Or cases where in the training side, you had a feature that was required. It appeared in all the training examples. On the serving side, you start seeing nulls on that feature. Again, something that is very common. Or even zeros, right? It's a little bit surprising how often zeros are the root cause of the problem. Because again, in many library calls that generate features, zero might be sort of the default value. So some feature stops being generated and zero is being returned. And the coder or the implementer of this particular library forgot to do error checking. So they just said, okay, I got a value back, I'll just take it as a feature value. So monitoring things like that can get you surprisingly far. And of course, now you have the long tail, right? Cases where bad things can happen and you need more involved techniques. But this notion of a schema, at least in the context of TensorFlow data validation, where we applied it, worked very well for production use cases at Google. So that's one concrete data point that I can offer.
Gotcha. That's really interesting. That's something that simple could catch so many potential bugs, and the examples you give are really really help us like imagine like all sorts of things there. One of the other
let me just
go ahead.
If I can qualify one thing though. So a schema is a good thing, right? I mean, it seems like a generally good idea. The problem is that not everybody has a schema, right? So we had teams using the model, and basically when we told them, hey, what is the schema of the data that went to the model? They basically said, we don't have access to it, or nobody bothered to write this down. It's all encoded in code. So we have to go and look at our code, understand which features we're pulling in and what are their types and so on. So the thing that we did that I think really helped here is that we told them, okay, don't worry, give us the data, we'll auto-infer the schema. Okay, so this goes back to this idea that you have to get people started with monitoring by providing some on-ramp that isn't just them configuring everything up front.
Gotcha.
And this on-ramp was, a good point to get them started about their data. In many cases, when we showed them the schema we inferred, they were very surprised. They basically said, wait, I didn't expect this feature to have nulls, or I didn't expect this feature to have weird values. For instance, one team discovered that when they were transcribing the language feature from something that the phone gave them as metadata, they were doing it the wrong way and sort of had buffer overruns. And they would see that some of the most frequent values corresponded to garbage characters. So this kind of data checking is actually surprisingly powerful in many cases. Yeah.
Gotcha. One of the things that story where you going to specific teams and helping them get set up, one of the things that makes me think about is kind of what is the role of the human in the loop for these future data-centric AI pipelines. I think very traditionally we think of ML engineers or maybe even data engineers. And I'm kind of curious, what do you see the role of the human in these data-centric pipelines going forward, whether it's maybe a specialized team at the center of Google that kind of helps everybody out, get their pipeline set up, get their monitoring set up, or if it's maybe more of the domain expert from like the business team who doesn't have as much expertise. Where do you kind of see the human play a role through all those different steps of the pipeline?
Yeah, I think there is a range of possibilities here, and this depends highly on the skill set in the company and the way that, in some cases, it reflects, the org chart in the company. But typically you have data scientists and ML engineers and human annotators as three distinct personas, right? And you want to involve them on different parts of the whole process. In the code-centric workflow that I described, for instance, the data scientist is still responsible for authoring the training code, and is also responsible for debugging the model, but it's not responsible for deploying the model, right, in production. The ML engineer in production will be the one who is sort of the frontline defense if something goes wrong. And that also changes the information that we need to expose to these different personas for their job, right? So the ML engineer will not be able to make sense of the quality metrics of the model or to understand necessarily what it means for drift to happen. What they will care about is that there is some alert, and if it fires, they have a way to roll back the model and say, look, this model is problematic, let's roll back to the previous version. Much in the same way that you have SREs, site reliability engineers, who run a service, and when something goes wrong with the service, they flip it back to the previous known good state, and they alert one of the developers of the service and say, hey, look into it, why this went wrong, right? So the ML engineer will alert the data scientist and say, look at this, why did it go wrong? The data scientist will have to investigate. Maybe it's a matter of mislabeling the data, for instance, right? In which case the data scientist now will have to interface with the human annotators and say, look, these are examples that have been mislabeled. Let's fix the labels. Let's retrain the model, right? That's one possible workflow. Now, in different companies, these personas might be merged. So you have companies where data scientists become empowered to deploy things end to end, right? So they author the models, and then they have some easy way to put them in production. You still need the infrastructure in production for all the stuff that we talked about: versioning, monitoring, automation, but you might be a little bit more opinionated on the infrastructure side because you don't have people looking at this infrastructure, right? And in other companies, you also have, maybe this very strict divide, or ML engineers who also play the role of data scientists. So if an alert happens, then they can sort of look at it in more detail as well. That used to be common at Google, for instance. There was a very clear separation between machine learning engineer and data scientist.
What are kind of the pros and cons of those personas being merged or not merged? Because I can imagine, in the one setting, there's probably imperfect communication, imperfect knowledge if they're separate roles, but you can also imagine a situation where if they are the same role, maybe one person is maybe overloaded, or they don't have quite the same expertise. I'm kind of curious about that division of roles and what it kind of means for the end product and the end solution.
Yeah. I mean, I think it's a matter of how easy is it to find this combined skill set of somebody who understands very intimately how a production system works and also how models work, right? And also, usually in production, you don't have a single model that you worry about. You might have 10 or hundreds of models running, and then you need somebody to be paying attention to all of them. So if you end up having a same persona that's doing both the production debugging and the model debugging, then you're taking away their attention from maybe the other models that have problems in production that need to be looked at. So this layering gives you the ability to triage and to sort of specialize, right? Which has its benefits. But then you have to sort of worry about the handoff protocols. What happens when the production engineer gives the data scientist an alert? How much information do you want to transfer over? Because there are cases also where data scientists don't have access to production systems. So now you're faced with this problem of, okay, the problem occurred in production, but I cannot give my data scientist the data that caused the problem. I have to give them maybe some chart that indicates what happened, maybe some statistics. So we go back to that last lesson that access is not always feasible. So that's where infrastructure comes in. You have to have these protocols, maybe you have data logging so that you can share data as needed. But it's, that's where the complexity arises.
Gotcha. Yeah, that's a really interesting problem to kind of bounce around and think about from an organizational standpoint.
Awesome. I think we're about at time. So I want to thank you, Alkis, for taking time out and answering all of the numerous questions that we had. Thanks for everyone for joining in as well on YouTube. And go to our website, mlsys.stanford.edu. We have a mailing list that you can sign up to, and we send out emails every week about the speakers that are coming on. As well as, on the YouTube channel, you can see all our past videos. We have a ton now, 65 and counting, I guess. And I think next week, who do we have, Dan?
Next week, we've got Roman, I think it's Katsinik from Meta. He's going to be talking about machine learning in production. Awesome. Yeah, so this is definitely been a back-to-back large company speakers coming in. Last week we had Uber, this week Databricks, next week Meta, so it's going to be exciting. Thanks so much, Alkis, again, and see you, everyone. Bye, YouTube. Bye, YouTube.